Alrighty, morning everybody. Welcome back to Calc 1. Plan for today is I have a quiz for you as promised on Standard 2, and then we are going to pick up from last class in our discussion of continuity, focusing today mainly on how can you determine where a function is continuous without necessarily being able to look at a graph of the function. Got my usual office hours for the next couple days. Today at 11 and 1, tomorrow at 10 and at 1. As far as homework goes, posted a new web work assignment for Monday. Don't forget you have one due tonight, and you have one due on Friday as well. Let's see, got a few retests to pass back. So, Emery, Jonah, Aiden Peck, and Lauren. So, I know we've already had this discussion, but I forget what the consensus was. You all want the joke of the day before or after the quiz? Before. You all were before. Okay. My other two sections both said after, I'm pretty sure. So, with that in mind, how can you tell if a clock is hungry? You can tell a clock is hungry if it goes back for seconds. Alrighty, and with that, I'm going to go ahead and pass out today's quiz. So, just like the last quiz, when you're done, you can just hold on to your quiz, draw a picture on the back of something terrifying. And once again, when I give, go ahead and take a few seconds to finish up your thoughts again. That means you have about 45 seconds left. I'll start this in today. Have fun. Quiz is out, so quiet in the room, please. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please.
Most terrifying. I got it. That should be an evidence of itself. Oh.
Thank you. Alrighty, so I'll get this quiz back to you on Friday. In the meantime, if you want to come ask for a retest of Standard 2 or Standard 1, you are welcome to do so. Again, just send me an email. Let me know which of my office hours you can make, or if you can't make any of my office hours, let me know when you're available so we can try and make something work out. After this week, I'm probably going to stop giving you so many reminders of this, so you have been warned. And I want to pick back up where we left off last time, where last time we talked about the definition of continuity. Yes? Did not bring any extra packets today. I tell you what. Shoot, I don't think I have this one posted ready. How about for today? Maybe you work with one of your neighbors from their packet, and then if you want after class, I can get you a packet, or at least email you one. So with that, let's jump back into continuity. So last time we talked about the definition of continuity, where a function is continuous at a value of x equals a, if three things happen. We needed that f of a had to exist, that the limit as x approaches a of our function had to exist, and finally that those two values were equal to each other. Meaning, if we have a function that behaves like this, would you say that f of a exists? Yeah, I would say so. At x equals a, we have this filled in dot up here. Does the limit as x approach a of the function exists?
Yeah.
I would say so. Looks to me like as x gets really close to a, we're going to get y values that are really close to whatever this y value is. Are those two values equal to each other?
No.
They do not appear so. F of a is way up here. The limit as x approaches a of our function is further down. So this would be an example where f of x satisfies the first two conditions, but not the third condition, and therefore is not continuous at x equals a. So last time we kind of focused on determining continuity from looking at a graph. We had this big example on the front page of our packet where you all looked at a big function, found the different ways in which a function can fail to be continuous, different ways in which a function can fail one or more of these conditions, in other words. And today I'm going to focus on what happens if we have a formula for a function, but we don't have a graph of it. Can we still determine where a function is continuous or not? And to start off, I'm going to be on the second page of the packet. We'll look at the function f of x equals x squared minus 9 over x squared minus 16. And what I would like to do is to see, can we find any values of x where this function is going to fail to be continuous? So to start with, does anybody have a value of x that they would propose as a value of x where this function may or may not be continuous? I did.
4.
X equals 4? Alright. What goes wrong at 4?
Because on the bottom it's x squared minus 16. So 16 minus 16 would make it over 0, so then it's undefined at that point.
Gadzooks. Yeah, we could say if we tried to evaluate f of 4, we'd get 16 minus 9 over 16 minus 16, which is 7 over 0. Does not exist. So right away, we don't even need to try and look at the limit as x approaches 4. Condition 1 has already failed at x equals 4. Yeah, Nora? I think for basically the same reason, x equals negative 4 is going to be another point of trouble. I know, I've taken English classes, I know my parts of speech. Yeah, for similar reasons, at x equals negative 4, if we tried to evaluate f of negative 4, we'd get 16 minus 9 over 16 minus 16, since 4 squared and negative 4 squared come out to the same thing. And x equals negative 4, I would agree, looks to be another point where continuity is going to fail, because our condition 1 doesn't hold. Are there any other values of x where you all would propose this function is not going to be continuous? No? Dang, no one's falling for my trap. Good, there aren't any others. In fact, x equals plus or minus 4 are the only values where this function is going to fail to be continuous. All right. Confession time. I have a dirty little secret to tell you. Most functions that you will see out in the wilds are going to be continuous wherever they're defined. If you ever have a polynomial, for instance, something like x squared minus 9, that's defined everywhere. That's going to be continuous everywhere for all values, for all real numbers x. If you have a rational function, which is like a polynomial divided by another polynomial, something like x squared minus 9 over x squared minus 16. That is going to be continuous everywhere it's defined, meaning as long as x is not equal to plus or minus 4 in this case, because you don't want to divide by 0. If you have a trig function, it's going to be continuous everywhere it's defined. If you have an exponential function, continuous everywhere it's defined. Root function, continuous everywhere it's defined. A logarithm, continuous everywhere it's defined. Right. A constant function, continuous everywhere it's defined. Most examples of functions that you've seen before probably in your lives are continuous everywhere that they're defined. Unless you have some sort of crazy function that it's really hard to find an actual formula for. So Dr. Gerstle, what would it look like if you have a formula for a function that's not necessarily going to be continuous everywhere it's defined? And for that, we're going to have to get a little bit funky. So let's look at our next example. I'm going to look at the function g of x equals 3 minus x squared if x is greater than or equal to 3 and it's equal to x minus 1 if x is less than 3. So this is a weird sort of function, in that depending on what type of value of x you're looking at, your function can do one of two things. We're used to working with functions that take in an x value, does the same thing every time to that x value, and spits back an answer, depending on your x. This is a function that sort of would be like if you were going to the post office and you sent in some mail, and the first thing the post office checks is this local or not local mail? And the local mail goes into one bin, the non-local mail goes into another bin. And they get treated differently. If we have a function like this, if you're plugging in a value of x greater than or equal to 3, it does one thing. It just spits back out 3 minus x squared. But if you were to plug in a value of x that's less than 3, it does something completely different. It spits out just whatever x minus 1 instead. Does anybody know what the name for this type of function is called?
Piecewise?
Yeah, it's oftentimes called a piecewise function. Where a piecewise function is just a function like this that's defined differently on different pieces. It has multiple pieces to it. The x greater than or equal to 3 piece, the x less than 3 piece in this case. And in general, with a piecewise function, there's no limit to the number of pieces you can have. You can have a function that has 2 pieces. You can have a piecewise function that has 3 pieces. If you're feeling particularly malicious, you can have a piecewise function that has 30 pieces. When I was a student in undergrad, one summer I worked on a research project where I had a 10-piece piecewise function, and it made me cry, quite literally. I don't think I'll be giving you all anything quite that bad, but you never know. I feel like sharing some tears with you all. And with a piecewise function like this, it sometimes can be a little bit more challenging to determine where is that going to be continuous and where is it not going to be continuous. So if I were to give you something like this and ask you, where is this function going to be continuous? Or maybe a better question, where is it going to fail to be continuous? What would your all's first thought be? At 3? Why is that?
Because it'll jump.
It'll jump.
Well, because you have 2 different functions. Because you have 2 different functions. I could be wrong. But they're 2 totally different functions, so they might be going different directions, even though they might line up. They might not. Does that make sense?
Okay, interesting.
Like that,
We might have something like that graph going on.
I think.
Oh, let's sketch a graph of this and see if and see what we can find. Because I think you might be onto something. So let's see. If we were to plug in values of x, g of x, where x is less than 3, well, to me that looks like we're going to have a line that y equals x minus 1, which will look something like this. And this will be at a height of, what's 3 minus 1? 2. Notice that I drew an open circle here instead of a filled in one, because this piece is how g of x is defined only if x is strictly less than 3. At x equals 3, we have to go to a different piece to see how is this defined. If we go to g of x equals 3 minus x squared for x greater than or equal to 3, so y equals x squared is a parabola like this. Negative x squared will turn that smile upside down into a frown. And then 3 minus x squared will just move that up by 3. So we'll have a downwards opening parabola. Let's see, at x equals 3, we'll have 3 minus 9 is, what, negative 6? And then just continue going downwards in a parabola motion like that. Fist bump that, Nate. So with that in mind, does this look like an example of a function that's continuous at 3? What condition or conditions fail from our definition of continuity?
The limit as x approaches 3 and x of 3, like the function at 3 are different.
Yeah, we have that. If we were to plug in 3, we would get an output of -6. We have to go to this piece because it's the x greater than or equal to 3 piece. And 3 minus 3 squared is 3 minus 9 is -6. What is the limit in this case as x approaches 3?
2.
It would be 2?
From the left it would be 2, and from the right it would be -6.
Oh, from the left it's 2, from the right it's -6. Gadzooks. So what's the overall two-sided limit going to be then?
It doesn't exist.
Yeah. So this would be an example of a function where condition 1 checks out. G of 3 does exist. We can get that from plugging 3 into the top piece here. But conditions 2 and therefore 3 are going to fail because the limit as x approaches 3 of this function is undefined. There is indeed a jump at x equals 3 in how it behaves. So, yeah, I would say that this function is not continuous at x equals 3. Are there any other values of x by which this function is going to be not continuous? I think everywhere else actually is going to check out. Because 3 minus x squared is continuous everywhere it's defined. It's just a straight line. Straight lines are always continuous. X minus 1, or no, that's x minus 1. 3 minus x squared is the downward parabola, and a parabola is going to be continuous everywhere it's defined. And so in general, when you're looking at a piecewise function like this, trying to find where it's continuous, where it's not continuous, the points you really need to check for continuity are points where you switch from one piece of the function to another piece of the function. So in this case, at x equals 3, we have a switch from one piece to another piece. And if we really want that one piece, we want to be king of the pirates, we have to... Sorry, I lost my train of thought trying to make an animated joke. We have to be careful and make sure that the function matches up on those pieces. Just for the sake of fancy, though, let's say we didn't have a graph to look at. All that we had was this formula, and for whatever reason, if this is something you didn't know how to graph. What could we do if we wanted to check, does continuity of our function hold at x equals 3?
Set the two equations equal to each other at 3 and see if they are equal.
Ah! Plug in 3 to both of these? But why would we want to plug 3 in here? This piece isn't even defined, isn't even used to say what happens at x equals 3.
Because it's still going to approach 3, so you're going to know where the limit kind of, like where the function ends at 3 and see if it meets up with the second one.
Ah, okay. So it sounds like you're trying to check for this limit. Does the overall limit exist by checking a limit from the left and the right? Let's do that. I think you have the right idea. So let's see what happens if we take a limit as x approaches 3 from the left and from the right in this case. So let's say I want to take a limit as x approaches 3 from the left. I'm going to look at if you plug in values for x like 2.9, 2.99, etc., what sort of y values are we going to be getting? So if we want to look at values of x as x approaches 3 from the left, values of x slightly less than 3, are we going to be plugging those values of x into the 3 minus x squared expression or into the x minus 1 expression? Why x minus 1?
Because that's all the values less than 3.
Any value of x less than 3, even if it's a value of x only a little bit less than 3, like 2.99, we would plug into the bottom expression. So what we would be getting is that the limit as x approaches 3 from the left of g of x is really going to be the same as the limit as x approaches 3 from the left of x minus 1. Because that's how g of x is defined everywhere to the left of 3. And how do we find the limit as x approaches 3 from the left of x minus 1? James?
You plug 3 in for x.
Yeah. This is a simple linear function. For something that's just a straight line like this, as x approaches 3 from the left, what happens to x minus 1? Well, x is getting close to 3, so x minus 1 is going to be getting close to 3 minus 1. And so we get a limit from the left as x approaches 3 of 2 in this scenario. So, on the flip side, what happens if we take a limit as x approaches 3 from the right? Meaning we're plugging in values of x a little bit bigger than 3, like 3.1, 3.01, etc. Which piece of our piecewise function are we going to use? Yeah, the top piece. Because this is how the function's defined, well, first of all, at 3, and also at all values of x greater than 3. So, in this case, we take a limit as x approaches 3 of 3 minus x squared. I again think this is something we can evaluate by just plugging in 3 for x. Plugging in 3 for x doesn't cause anything sinister to happen here. And it appears we get a limit from the right of negative 6. And so, our function has a limit as x approaches 3 from the left, g of x goes to 2. From the right, g of x goes to negative 6. So with that in mind, what's the overall limit as x approaches 3? It doesn't exist. So we can say since limit as x approaches 3 from the left of g of x is not equal to the limit as x approaches 3 from the right, the overall limit as x approaches 3 does not exist. And therefore, condition 2 is going to fail. And so we can automatically say, thus, g of x is not continuous at x equals 3. So the moral of the story is, whenever you have a piecewise function and you're checking for continuity, you always need to check the points at which you switch from one section of the domain to the other section of the domain. Because you could have a scenario at x equals 3 where on one side of your switching point, your function behaves very differently than on the other side. And if that happens, then you would say your two-sided limit doesn't exist, therefore your function fails to be continuous. On the other hand, if these two values had come out to the same thing, then we would have said, oh, limit as x approaches 3 of g of x does exist. And then if we would check to see is that the same as what we would get at 3, and if so, it could still be continuous there. Any questions, comments, or concerns before I set you all loose on a couple practice problems? Alrighty, so in that case, If you flip to the third page of the packet, I have a couple more piecewise functions for you. And what I would like for you to do is, as usual, talk with your working with your neighbors. See if you can find all values of x where these two functions, this h of x and this gasp k of t, are going to fail to be continuous. Let's go ahead and take a couple minutes, work on that, and we will come back together as a class to look at this.
Yeah, but first, or wait, no, x doesn't equal here, so that you don't have to worry about that extra like, so you don't have to worry about this being right here.
Oh, right, okay.
Yeah.
Okay.
No, we could do.
You can still just plug it in, or you can plug it in, you can factor it.
Yeah, we can still do that.
Then just put the limit equals. So it would. The big thing.
Let's go. You think you got it? Yeah, to the bottom one we're just factoring out. Or I grab that right here just to get extra. And then plug it in, they can do it, you know, so you get the same thing. Oh, they do? Yeah. They do get the same thing.
As always, feel free to flag me down if you and your neighbors are unsure about something.
But that's why it's like not a negative two. Like there would be a, like if it was just this, then there would just be a straight. Whereas this, if this then equals, and then it would be continuous because.
So then what we try is rule going up over the equals there, but then you're looking at it actually equals.
All of these values aren't in page 9.
They equal the same thing.
Yeah, so
And
you
then when
need
you
to
do this one, it's
set them equal
exactly
to each
Right.
other.
Yes, I did.
Okay.
For sure.
Yeah.
You figured out
So I
first.
think it's I think you have to do the same thing.
Yeah.
Just do it as. Limit. I think we have to put it in the top one, like take the limit of that as your best. And then save the. Yeah, and then find it as and see.
Yeah, so
The second one's similar, you just have to do it with two of them. First one. You get that?
yeah, so then are there no points with this is
I think so.
This one would be continuous, like it's set in together.
It is a little bit weird that I would define it that way,
Yeah.
but I did it that to make a point.
Yeah.
I guess that's one way to, if you want to be continuous at
So these two.
It's weird to have a formula, and you could just say, oh, it's negative, y equals -1 there.
Yeah.
Alright, in most cases you would not see something like that occur at a single point. Here's a complicated formula.
Right, equals that 1 point.
If I make them equal signs because I don't see the bottom.
Yeah.
So then I
It's
make
like
this, yeah.
Yeah, instead of like.
Well, I love it.
And then it does this guy on the
Yeah,
wall.
it's not really a sign, but yeah.
Take about another minute and then come back together to discuss as a class. Find out values of x for this function fails to be continuous. That sounds like some coordination. I refuse to do this next week. Oh, there are no fun ones, I see. Just,
I refuse.
just no.
I refuse.
You used to do anything you want in this class. On your head piece. Okay, I want to come back together now and take a look at these two functions. So walking around the room, heard some good discussion going on of places that are suspicious, places that we should check. And I think a good first step in looking at any sort of piecewise function like this, if you're trying to determine where is that function continuous, is to check for suspicious points first. So in this case, are there any values of x looking at this piecewise function that are, dare I say, suspicious? Potential places where this function could fail to be continuous. Or is it super obvious, it's like, Dr. Gerst will clearly look at this, clearly it's continuous everywhere.
-2 suspicious.
Yeah, -2, at x equals -2, we sort of have a switch. At everywhere other than -2, it behaves one way. At -2, it behaves a different way, potentially. So, let's say x equals -2 is a suspicious looking x for me. So, first of all, is f of -2 defined? Does condition 1 check off here? I would say so. If we plugged in -2, our function tells us if you're plugging in -2, do this. An absolute value of -2 minus 3. Gadzooks, what is this absolute value telling us to do to -2? That's right. Yeah. Absolute value, you put the vertical bars around a number. If it's negative, you make it positive. If it's positive, or 0, you leave it alone. So in this case, that would just become +2 minus 3 is -1. So I think condition 1, is going to check out. Condition 2, we need to check to see, does the limit as x approach is -2 of this function exist? So I have a question. Do we need to take a limit from the left and a limit from the right here? I think we certainly could. But I also think in this case, we don't need to take the limit from the left and right separately. We can just take the overall limit all at once. Why is that? Dr. Webster's up to his usual tricks. So why is it in this example, unlike the previous example, we can take the limit from the two-sided limit instead of having to worry about breaking it up into left and right hand?
It's because it's the x squared plus 3 plus 2 over x plus 2 on both sides of the -2, so it's continuous everywhere except the -2, so it would be pointing to the same spot if you take the limit.
Yeah, I would say at x equals -2, our function behaves, we have a different piece for our piecewise function, but we're using the same piece to the left of -2 and to the right of -2 in this case. We're using this bottom piece here. Whereas in our first example, at x equals 3, we had the function using different pieces to the left and to the right. So in that case, we needed to take our left and right hand limits separately because they could be different from each other. In this case, I don't think we necessarily need to worry about that because the function behaving the same to the left of -2 and to the right of -2, it's just behaving differently at -2 itself. So if we want to take a limit as x goes to -2 of h of x, well, I think that's going to be a limit as x approaches -2 of this expression, because whether x is approaching -2 from the left or the right, you're going to be getting y values by plugging values into the bottom piece of the piecewise function. And how are we going to evaluate this limit? The limit as x approaches -2 of x squared plus 3x plus 2 over x plus 2. I don't think we can plug in -2 here for x because we get 0 over 0 equals sad. Jennifer?
You can factor it to x plus 1, x plus 2, top.
Ooh! X plus 1, x plus 2. Let's see. That'll give us x squared plus x plus 2x, so that's plus 3x plus 2. The foiling checks out there.
And then you do your swipe thing.
Do the old swipe thing. Swipe or no swiping. Or as I like to say, swoosh swoosh.
Oh yeah, swoosh thing, I said that.
Yeah, get it right. Okay, and then what do we do from there?
And you can plug -2 in now.
Yeah, because the x plus 2 factors cancel out. You can just plug -2 into x plus 1. And it appears that we do in fact get a limit that exists of -1. Imagine that. So condition 2 checks out. How about condition 3? Does f of -2 equal the limit as x approaches -2 of our function? Does -1 equal -1, in other words?
Let's see.
Let's see. I hope by the end of the semester I've trained you all to think every question could be a trick question. That being said, this one is not a trick question. The limit as x approaches -2 does in fact equal at h of -2 in this case, because both of these values we got are -1. So with that in mind, let me ask the same original question. Are there any values of x at which this function, h of x, fails to be continuous? Nope. It's continuous at -2. There aren't any other suspicious points. This thing's going to be continuous everywhere. We apologize to x equals -2 for calling it suspicious, when in fact nothing was wrong with it. Turns out this is a nice, smoothly, well-behaved function, even though it has multiple pieces, including some shadiness going on at x equals -2. Turns out the shadiness was totally above board, government sponsored. A because we know that our function is continuous at -2 because f of, or well not f of -2, actually h of -2, the limit as x approached -2 of our function both existed and were equal. Any questions or comments about this h of x function? Let's look at this k of t function then. So this is our first three-piece piecewise function. Are there any values of t here where that looks suspicious? Just looking at the three different pieces to this function. Meaning, are there any values of t that we need to give special attention to in checking for continuity?
One and -1.
Yeah, I would say 1 and -1, because at those 2 points the function behaves differently than it does everywhere else. So in this case, we actually have 2 points we need to check and go through. Do the 3 conditions hold for continuity? Let's see. Hey, which one do you want to check first?
Let's do -1.
All right, let's check t equals -1. We're going to go through both of them, so the order in which you check them out doesn't matter. So, first of all, let's go through condition 1. If we plug in -1, does k of -1 exist? I would say so. The function quite literally tells us that if we plug -1 into the function, we get 3 as an output. No computation necessary there. It just says, you plug in -1, here, have your 3. Unlike this example where we had to do some actual computation at -2. All right, so next. So first condition checks out. Second condition, does the limit as t approaches -1 of this function exist? Do we need to take a left and right limit separately, or can we just do a two-sided limit here? Right?
Two-sided.
Why can we just do a two-sided here?
Because it's the same one for both of them. Like if you were to do it from the right or from the left, it would be the same.
Yeah, it's because we're using the same piece to the left of -1 and to the right of t equals -1, namely this top piece here. If instead we had, if t is less than -1, it behaves like this, but at t greater than -1, it behaves like that, then we would need to do left and right limits separately. But in this case, just like with the previous one, on both sides of -1, we would go to the same piece of the piecewise function. So I agree. I think we can just do a two-sided limit here. So we want to take a limit as t approaches -1 of k of t. Well, if we're plugging in values of t that are close to but not equal to -1, like -0.9 or -1.1, looks to me like we'll be plugging in values of t into this top piece here, because we'd be plugging in values of t that are not -1, and also probably not 1, because 1's not really close to -1 per se. How are we going to evaluate the limit as t approaches -1 of this booger? I apologize if my coarse language offends you. James?
We can actually just do it like normal, or we can factor it first. Because it's -1, so it doesn't leave a 0 on the bottom, so you can just plug in -1 for all the t's.
So when you say do it like normal, you just mean plug -1 in?
Yeah.
Yeah. In this case, actually I think this expression's pretty nicely behaved at -1. we don't have to worry about dividing by 0 or anything, unlike in that previous example. So we can just literally take -1 squared minus 4 times -1 plus 3 over -1 minus 1, which is going to give us 1 plus 4 plus 3 over -2, which is 8 over -2. I'm getting -4 as my limit. If we had done the approach where we factored the top numerator and did the old swoosh swoosh on the common factors, I think it would have come out to the same thing. So limit exists, function exists. We have to go to condition 3. Does k of -1 equal the limit as t approaches -1 of our function? In other words, does 3 equal -4? I would say no. K of -1 in this case does not equal limit as t approaches -1 of k of t, and so we would say our function is going to be not continuous at t equals -1. It passes the first two conditions. The function is defined at -1. The limit exists as t approaches -1, but those two values were not equal to each other, so condition 3 for continuity failed for us. Any questions or comments about that one? So our first suspicious value of t turned out to actually be evil. But we have another one to check. We also have to check t equals 1. The big brother of t equals -1. So, first of all, does k of 1 exist? Well, the function literally tells us what k of 1 is. It's -2. So, that checks out. Again, I think we could just do a two-sided limit here as t approaches 1, since the function behaves the same to the left of 1 and to the right of 1, namely using this top piece here. So I can take a limit as t approaches 1 of k of t is going to be equal to the limit as t approaches 1 of t squared minus 4t plus 3 all over t minus 1. And can we just plug in t equals 1 into this expression like we did with -1? Why not? Sadness? What sort of sadness ensues if we plug in t equals 1 into this expression? The sort of sadness where we divide by 0. So I think in this case, we are going to actually need to go through and factor and cancel out common factors. So let's take a limit as t approaches 1 of this expression by factor. Can anybody tell me how t squared minus 4t plus 3 is going to factor?
T minus 3 times t minus 1.
T minus 3 times t minus 1? Let's see. T squared minus 3t minus a t, that'll give us a minus 4t. And then minus 3 times minus 1 is plus 3. Jonah, what do we do next?
Oh, swoosh, swoosh.
That's right. Swoosh, swoosh.
I got it right that time.
You did indeed.
Let's go.
Alright, don't get too full head. And now we can just plug in t equals 1 into what's left. We get 1 minus 3. Oh, hey. You got -2 as our limit. does condition 3 hold? Meaning, does what you get when you plug in 1 equal what you get if you plug in, if you take the limit as t approaches 1? Sure looks like it to me. Both of these are coming out to -2. So we can say that both k of 1 and the limit as t approaches 1 of our function are both going to exist, and they're both going to equal -2. So it turns out we have to apologize to t equals 1 for putting it on the suspicious list. Because this function is continuous at 1. In fact, the only value of t where it's not continuous is at -1. Because at t equals -1, the limit did not match up with the value of the function at -1. So conditions 1 and 2 worked at -1 but not 3. Whereas at t equals 1, all 3 conditions held, the function was defined, the limit existed, and they gave us the same value. So that is how you would check a piecewise function for continuity. You kind of have to look at all the different points where you switch from one piece to another, and then just go through your 3 conditions. Oh, packing up as if there's not like a good 2.5 minutes left in class. For shame. Any questions or comments related to either of these functions? Alright, well I was going to let you go, but if you're packing up on me like this, I have half in mind to keep you around. Alright. How many of you know how to teleport? I had a student who did research this summer on how to teleport. True story. Our next topic is how can we have functions that teleport, if such a thing is possible. And for that, we will wait until Friday. So when we come back on Friday, we're going to finish off standard 3. So you can plan on there being a standard 3 quiz on Monday. Have a good one, everybody.